How many were? 10. Maybe one more minute. I have my coffee.
Hello, Professor.
Hi, nice to see you.
Nice to see you too.
Let me drink it up to the very end for your health. And
Take your time.
okay, so let's start. Um, Today we will play with this I have to switch off. Just a second. On purpose, I didn't look my emails today. Okay. Um, we discuss more the polymer solutions, and we start where we stopped. So we considered the osmotic pressure. So we introduced the Fleury-Huggins model, which is an okay model for polymer solutions. We said it's okay, no more than okay, but okay. You can start from this and make it better, but then you immediately get complex theories like the Bavendi-Fried one, and this is not what we want to do in this course. So let's stay within the model. The model showed us, however, something very funny. We will discuss what really happens there in a semi-dilute regime a little bit more during the tutorials. But one unpleasant thing we have already seen. This is that when you use the model without thinking, but simply use the model, for the solutions or the solvents which can get poor, for example, by lowering the temperature, suddenly you get the negative pressures. And the negative pressures are forbidden by the theory of thermodynamical stability. So this means that not that we have to improve the model considerably, but we have to be a little bit more cautious about what kind of systems do we really describe? What kind of thermodynamical situations do we really describe? Now, this is the following. It might be that when your pressure gets presumably negative, something happens with your system and it phase separates. Now in thermodynamics, there is a theorem, and this is the Gibbs phase rule. So you have a two-component system, and then essentially it can have two phases of the same aggregate state, which means they can be two solutions, and they might phase separate. So this means that when you act on your system and change phi, and phi is essentially within the model the only parameter to which you have the access, the system may go from a single phase situation, which means a homogeneous solution, to a two-phase situation, which are two homogeneous solutions. And now let's have a look what kind of these two homogeneous solutions can be attained, and when does it happen? Under what conditions does it happen? So I start here from the normal Flory-Huggins free energy divided by n, and this I call this function small phi, and for a single phase solution, the free energy is simply n times this phi up to the offset, which we neglected because there was some offset in the free energy from the entropic part. If you have two phases, you have two such functions phi. Now, the first question I put will be under what conditions the system will inevitably phase separate, which means under what condition a whatever two-phase situation is better than a homogeneous solution. And now, you know, I try to use my iPad and to draw a simple picture. So I have, okay, this was relativity theory. Let's leave the relativity theory aside. Let us assume we have a vessel. And we have our polymer solution in this vessel, or whatever other solution. Now, let us consider the simplest situation. So we said that there are some conditions under which the system will inevitably phase separate. A whatever phase separated situation with here phase 1 and here, let's say, phase 2, is better than a homogeneous case with only one phase. Now, what are the conserved quantities here? The conserved quantity is the total number of molecules, whatever, both the polymer molecules and the solvent molecules. So if some molecules, for example, here I have a polymer poor phase, which means that the molecules travel from this upper part, so to say, into the lower part. And here I have a polymer rich phase. So here I have many molecules. And here I have only few. The total number has to be conserved. Now, as my reference situation, simply to keep things simple, because I'm looking for conditions where a whatever other situation is better than homogeneous solution, I say that the volume of this guy is V half, sorry, and the model of this guy is V half, which means the number of sites in the first half and the number of sites in the second half are the same. And now I can stop this and I can go back to the script. Just a second. Okay. So if I do so, if I take each of the parts having the total number of sites, which is exactly 1/2 of the full number of sites, then the concentration in one would be the number of monomers per site. Phi plus delta, this will be polymer rich, and this will be polymer poor, phi minus delta. And these deltas are the same. Now I compare this situation with the homogeneous solution, which is N0 phi of f of phi and I. And if this guy is larger than this guy, the system doesn't have to phase separate. If this guy is smaller than this guy, if delta F is negative, the system will inevitably phase separate, because as my phase separated reference state, I took an arbitrary one. I don't know whether it's the best thing to phase separate into two phases of equal volume with the concentrations which differ by that. Now I expand this guy into Taylor series, and I see that the first non-vanishing term in this expansion is second order in delta, and it contains this second derivative here. Now, do you understand why? This is a question.
No, I did not.
No. Okay. I think it is quite trivial, but I will show it. Essentially, I showed it later in the lecture once again, but let me now again do it in a very simple way. So what I have there is the expression of the type, I have some function f of phi plus delta. I don't put high here. High is constant, plus f of phi minus delta half minus f of phi. And let me assume that my delta is small. Because I am free to create a whatever reference state I want to. Each state is better than the homogeneous phase. Now, let me assume that delta is small and start expanding this into the Taylor series. I will have here f of phi. Okay, let me put 1/2 in front. F of phi plus f prime of phi delta plus 1/2 f double prime of phi delta squared. Now the second term starts, plus f of phi minus f prime of phi delta plus 1/2 f double prime of phi delta squared plus blah, 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 and then minus f of phi. Now let's have a look what happens here. I have this f of phi and this f of phi with 1/2. It gives me f of phi with plus, and this guy is with minus. So these three terms cancel out. Now let's look here and let's look here. They have the opposite signs, so they cancel out. So what stays in the lowest order is this guy with the second derivative. So now, just a second, okay. Now, let us go back. So I have this guy with the second derivative. And if this guy is negative, which means if delta F is negative, the free energy in the phase separated state is smaller than the free energy in a single phase, the system will inevitably phase separate. Now here I do exactly the same. I show that this that saying that I have the two states of the same volume with the same delta is not necessary. Why do I show it? Because I will need this calculation later. I don't have to discuss it now. I can come back to it later. The only thing is that the only important thing is here is the following. This is the conservation. Let's assume that the concentration of monomers in one part of the vessel is phi1 and in the other part of the vessel is phi2. Then I have this total conservation law. This is the conservation of the total number of particles. And this gives me automatically the fact that the deltas, the differences in concentration in the two phases, that these deltas are connected with each other. And now if I assume that the system phase separates into two different volumes, I get here this expression, but this expression gives me exactly the same condition for necessity of the phase separation. Why? This is because x is always between 0 and 1. X is a part of the volume occupied by the first phase. Any phase cannot occupy less than 0 or more than the whole volume. So this is non-negative. And this is exactly the same second derivative. Okay, now I will use these expressions later, therefore I put it here. So when does this phase separation start? Now, let me stress that why do I not describe not discuss even the situation where there are 3 phases, 4 phases, and so on. This is because of the Gibbs phase rule, which says me that if I have a solution, 2 component, single phase, I mean single aggregate state, there are at most 2 phases. Now, the transition between the second derivative positive, second derivative negative, passes through a line at which the second derivative is 0. And this line is the line on which the phase separation inevitably starts. It starts when I cross with my high from low values to high values. Now I can calculate this second derivative from the Flory-Huggins. So I calculate here the first derivative and then the second derivative. Now I hope you can calculate it yourself. Or do I have to show once again? Because you first take the first derivative and then you take the second derivative. Do you need my help on this? No. Okay.
I'm okay.
You're okay. So if I take the second derivative, essentially a very simple expression stays. And I put it as an expression for high of phi. I have here a parameter. I calculate the second derivative, and then I express high via phi. So I have here, look, if I take here the second derivative of the guy, I will get here high, and this gives me 2 other terms, and then I say, look, I see that this high at spinodal is a function of phi. The second derivative of this guy is exactly minus 2 high, as you can see. So, and this is the structure. Now I plotted it for, so to say, hypothetical polymer of 100 repeated units, because otherwise you don't see the details. And you see that this spinodal has a minimum. Close to the minimum, it's a normal quadratic function, because it has the function which is drawn here has all possible derivatives. And it grows approaching 0, and it grows approaching unity. essentially indefinitely in both cases, and has a minimum somewhere. So this means the following. If I start at high temperature here, this is 1/2, so I start somewhere here, I am in a solution which can get poor at low temperatures. So I start at high temperature, at some value of phi, here, whatever. You are above 1/2, and then lowering the temperature, you come up to a spinodal. What happens before the spinodal? Who knows? We will discuss it. What happens above the spinodal is clear. Your system phase separates into a polymer-rich and polymer-poor domains. And essentially, you know, there are nice experiments also with immiscible low molecular weight solvents and so on and so forth. And all this theory of multi-component, multi-phase system, the whole metallurgy lives on this, and a large part of chemistry lives on this. This you probably know. And we have a very simple model, 2 phases. So here you can have 1 phase, or you may have 1 phase. Here you always have 2 phases. Now, if I look at this curve, it has a minimum. And the minimum is here, where the derivative of this high, which gives you the value of Flory-Huggins parameter on the spinodal, has its minimum. I can calculate the minimum, differentiate the function here, and put the derivative to 0. It's again not really a complicated art to differentiate the function. So you get minus 1 over n squared, and here you get 1 divided by 1 minus phi squared, but with plus because the derivative is negative, and you put it to 0, and this is what you get. What does it mean approximately? This is because I take n here to be large. You can have a look what happens if n is not large. You solve a quadratic equation, and then you can approximate the solution when n is large. Once again, do I have to show this, or I don't have to show this?
No needs.
No need. Great. So this is school mathematics, essentially. So what I see is that the critical point is situated on the high axis at 1/2 plus square root of n. So if I would draw here 1/2, yes, it will get here, this is 1/2 plus square root of n. My square root of n is here in this picture 1/10. So it's 1/2 plus 1/10, 0.6. And in phi, it is situated at 1 divided by square root of n, which means at 0.1. So the minimum is here of this curve. It's very flat here, and it's essentially flat for polymers. But if you zoom, you will see a normal quadratic minimum, as every twice differentiable function does have. What happens in critical point? Here the phase separation, inevitable phase separation, starts. Now, I put it here like this. Again, it might be necessary for some cases, but essentially it's simply a curve having a simple quadratic minimum. Now, a more complicated and also maybe a more interesting thing starts. Let us now have a look when does the two-phase situation lose its stability? So what we considered when looking at the spinodal is when the one-phase situation inevitably loses its stability. And now I'm looking at the situation when a two-phase, I'm going down in high in the Flory-Huggins parameter. I'm passing here. So here I have two phases. Yes, here I have two phases and I never have one phase. Here I cross the line, and here the only thing I can say is that I can either have one phase or two phases. Who knows? So now I'm interested in the opposite situation. When do I always have a single phase? And there will be another curve which we discuss now. When do I have a single phase? I have it in the case when a whatever two-phase situation, which means the optimal two-phase situation, which means a two-phase situation with total minimum of free energy is worse than the one-phase situation. And here I will discuss the approach, and then I think I had a picture in the lecture, and for the simplest case, you will get this for a binary alloy where the problem is really easy. You can solve it in the homework. And for a polymer, you know, you get two equations. You can put down the two equations, and then you have to solve them numerically and to draw pictures. And once I solved it numerically and I have drawn pictures, but I don't know now where the pictures are. You know, so many computers I used to have since I first gave the course. So some of the pictures are lost. Now, let us consider the optimal phase-separated state. The global minimum in the phase-separated system, provided you took the best two volumes and the best concentrations in them, so that the free energy of this two-phase system is indeed minimal. Do I have to explain more here or try to draw a picture like a picture I have drawn at the beginning? So you have now two sub-volumes of different size and with different concentrations. However, you have two conservation laws. The total volume is conserved. You still have the same vessel. And the total number of monomers is conserved, and also the total number of solvent molecules is conserved, because the molecules do not disappear anywhere. And now you have two parameters. X, it's a part of volume occupied by one phase. X2, this is 1 minus X. It's the total volume or total part, total share of the volume occupied by another phase. And you have the two concentrations which are connected to each other by the molecule conservation law. And this is what I put in blue in the first part of the lecture. So this is exactly what we were discussing there. So now I'm here, and I'm looking at the minimum of this function. I have now delta 1 and delta 2, which are connected by the relation which we discussed the above. If you look here, you see that the phi's or the deltas, which are phi1 minus phi and phi2 minus phi, are connected to each other, or if you want, here I have phi1 and here I have phi2, which are connected with each other by this statement. And the volume of one phase now consists of n0x sides, and the volume of the other phase now consists of n0 1 minus x size. And now I have to minimize this function. To minimize this function, I have to differentiate it both with respect to delta, which is a free parameter, and with respect to x, which is now the free parameter. So I can differentiate. Differentiating with delta gives me the phi derivatives of this function f. These are the first derivatives. I'm looking for a minimum. Put here 0. So this would be a minimum, if it exists, of course. And then the second time I differentiate over x. Here I simply rewrite. I will comment on these two expressions in a minute. I get this expression. Now I have two equations. I have this equation and this equation with two unknowns. These are two algebraic equations because the first derivatives of this Flory free energy per side of this small f are essentially the functions of the type of polynomial and simple. If we look at the Flory function, so what we see, we can see what the first derivative of it is. Let me just have a look at the Flory function. So here you get the first derivative. This one is high minus 2 high phi. Here I will get one thing is simply a number, it's unity. Then I will get here minus log 1 minus phi, and here I will get 1 over n log phi divided by n. So it's a function, but it contains polynomial and logarithmic terms, which means it's awkward, and you have to solve this system of algebraic equations on a computer. And then you get a curve. And this curve is the coexistence curve. I will discuss it in a second. But let me tell you, what do these two equations really mean? So here I get that the phi derivatives of phi1 and phi2 of this function f are equal at the coexistent curves. And here, these are essentially the volume derivatives put in an awkward form. It's not awkward, it's the best for the solution, but maybe a bit awkward for understanding. But let's try to understand, where do the equations stem from? The derivatives in phi can be translated into the derivatives with respect to the number of monomers, or if you want, to the number of polymer molecules, because these are simply the number of monomers divided by n, by the polymerization degree. And phi is connected with the free energy, because it's a free energy per side. Forget the offset, which does not depend here on anything. Might depend on temperature, but otherwise is fully uninteresting. What is thermodynamically a derivative of a free energy with respect to the number of particles? Who knows? Guys, chemists. Everybody has forgotten? Do I have to write something? Do I or do I not? You know what the derivative is.
Is it the chemical potential?
It's the chemical potential. And another one is the derivative with respect to respective volume, which means it's a relative of a derivative of free energy with respect to volume. What is this? Again, chemists and even physicists. What is the derivative, for example, in a gas of a free energy with respect to volume? It's the pressure, lecture zero, so to say. So what these minimization equations tell me are the two standard requirements for chemical equilibrium. And one is that the chemical potential of species, essentially of all species, in both coexisting phases has to be the same. In my case, I require that chemical potentials for monomers or for polymer molecules in both phases are the same. And the second condition is a condition of mechanical equilibrium. The pressures in two phases are the same because the phases have a border. If the pressures will not be the same, the border could move and would move. So I have just well-known trivial conditions for chemical and mechanical equilibrium. Now, I can do it. Now let's have a look. Essentially, this is described here. And now, in order to have the solution, you have to be in a situation when your chemical potential, which is proportional to the derivative of this function with respect to phi, is non-monotonic. If it's monotonic, you cannot have the same chemical potentials at 2 points. What does it mean? It means that the derivative, this derivative, has to change the sign, the derivative of chemical potential. This means that the second derivative has to change the sign. When does the second derivative change the sign? Below the spinodal. So this situation corresponds to some curve which lays below the spinodal. But of course above the critical point, because there, as we will see, the single phase always wins. Now, the second thing are the pressure, so to say, conditions. And from these pressure conditions, we essentially get that the 2 points here with the derivative, because both equations, this equation and this equation, contain the derivatives with respect to f. The derivatives are the same, but you have the additional condition here that both points, if I have my f of phi, both points at which the derivatives are the same lay on the same tangent. And this is a condition which gives you a curve, the coexistence curve of your system. This is a very typical picture which explains how how can I obtain the form of the coexistence curve graphically from the picture of f of phi. This consists of two branches at which you have a common tangent to your curve. Make many such graphs, but it's the same as graphical solution of my system of two algebraic equations, which is awkward. So now I have two curves. I have the spinodal here, above which I have always two phases. I have the binodal or coexistence curve, below which I always have homogeneous solution. They two always, one can show it also mathematically, the two always coincide in the critical point, and in between there is a coexistence domain. And in my system, this coexistence means that I can have either one phase or two phases. And it depends essentially on where do I come from. If I come from a homogeneous solution, I cross the coexistence curve normally into a metastable state. This metastable state means that the two-phase situation is essentially already slightly better here than the one-phase situation. Here, the two-phase situation is always worse than the one-phase situation. Here, it is slightly better, but it cannot, at least immediately, appear spontaneously. So the system is in the metastable state. The homogeneous situation is still a local minimum of the free energy. And the phase separated situation is another local minimum, which is essentially deeper. It's already a global minimum, but it's not easy to pass from one to another without strong perturbation of your system. So what you will typically see is that you come with single phase, you stay with single phase until you approach the spinodal, and then you phase separate on the spinodal. If you come from the two-phase region, from above the spinodal, and go down, here again, nothing happens because a two-phase system is worse. Is better than a single-phase system. So you stay in the two-phase until you come here when the two-phase system simply gets bad. Instead of having another local minimum of the free energy, you lose it. Instead of it, you have a point from which you can go by changing the concentrations to a better point in a single-phase situation. So here, single phase metastability, stable two-phase. Here, stable two-phase. And then, booms, at point 1. So, okay. Now we can also consider using exactly the same approach. It's over, but essentially I can start the second lecture immediately if you want, or if you want, we can discuss more, or if you want, we can make a break. Now it depends on you.
I vote for a break.
Then, you know,
Yeah. Break.
you are also for a break. Then let's make a break, but let us meet. When do you want to meet?
12:25 or something.
Okay, you know, if we will. Okay, let's meet in half an hour. So we meet in half an hour. I can have my sandwich and my coffee. And then today we will finish earlier, but this is not bad. Tomorrow is another day. Okay, so now I stop this and I will leave. No, I will even not leave this meeting. I will simply switch off video and radio